Hello and welcome to Toddcast number 48. We're going to continue on alkyne chemistry. This time we're going to look at new alkyne reactions. So last time we focused on ones you'd seen before. This time you've seen the reagents, but what they do with alkynes will be slightly different than what they did with alkenes. But if you know your alkene chemistry, you have a pretty good idea what's going to happen with the alkynes. So we did hydrogenation, H2, in some metal catalysts, such as palladium, platinum, cobalt, rhodium, etc., for alkenes. Ends up, they also react with alkynes. Makes sense, it's a pi bond. So H2, again, just to reiterate, you have a metal, it's supposed to be, let me draw this a little bit better. So I have a metal, and on the surface, the H's start to accrue. So the catalyst picks a bunch of H's. And again, to maximize surface area and not lose this, we put it on a carbon support, carbon solid. So bracket C, if you see that, simply means it is on carbon. Okay, so we have this, the alkyne, and then we also have another pi bond here that's not been affected, but this and this can interact, and that molecule can pick up two H's. But keep in mind, it is going to be syn addition when you use H2 on the surface of metal. That just becomes important. Okay, going to clear my picture. That's just revisiting what we saw with alkenes. It ends up they do the same thing with alkynes. Internal alkyne, meaning again, it's between two carbons. Terminal means it would have an H dangling off the end. So we end up in a situation where the two H's add in a syn fashion and force the alkene into a cis orientation for the other two groups. A terminal alkyne, exact same thing as internal, except instead of an R group over here, we have an H. Same story, we're going to add two H's across the pi bond. They're going to add in a syn addition fashion. We'll have no idea how to prove it because if you end up with H's here and here, then you don't know which one came on from which. So you just have to know mechanistically from the previous example or just how things work. That's what we have. Okay. Um, this works on either of these. Want to emphasize a couple things here. So H2PT worked with alkenes. The barium sulfate is known as a poison. So it ends up binding in such a way where the H's bind to the alkene, or onto the pi bond of the alkyne coming in, but they stay bound to that now alkene. And because of that, it can't orient in position to take on two more H's. So it poisons it and stops it at the alkene. Um, there's other ways of doing it. Different poison. Calcium carbonate is very similar to barium sulfate. When it's calcium carbonate, it's called Lindlar's catalyst. The reality is Lindlar's catalyst, there's a couple different versions of it. So just know that palladium or platinum with a poison and H2 will stop in an alkene. If you don't have the poison in there, so we just have H2 and platinum on carbon instead of with the poison version of it, then it will keep on going. It'll add again. Now, here's something I want you to investigate really carefully if I've done my H's correctly or incorrectly. And the first notion is to rotate it around, get it all to line up correctly, make sure. But I want to take advantage of this moment to just point out kind of a cool way to do this. So first off, these ends are syn, and these two groups are cis. So syn addition, cis, and then this reaction is also syn addition. So anytime you get syn, 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 then you should get everything on the same side. So it should be H, 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 and then R group and R group. Okay, that's where everything is cis or syn. So two H's, two red ones came together and back, two blue ones came together in front. These two groups are there. But notice that these two R groups have been rotated so that they're, I guess, pointing as far away from each other for steric purposes. Makes sense. The molecule would want to do that. But to get from here to here, up here, it has to rotate. So everything that is cis is now, when you rotate by 180, has to be trans. So if I rotated this, I'm going to keep the left side the same. And on the right side, I'm going to go with that. And it's the same as this, 3 carbons. I've just drawn it in a slightly different way. So this went from down to up. The H was up and in back, now has to be down and in front. And the H that was up and in front now has to be down and in back. Okay, so the key thing I'm going to note in this case, these were cis, cis, and cis. When you rotate, everything now becomes trans, trans, and trans. So quick and easy way to tell. If it is syn addition to something that's cis, then you should maintain that symmetry, that cis symmetry. Trans to trans, anti to trans, would be the same as syn to cis. So all cis or all trans is simply a rotation. So now we got to look a little more carefully at this molecule. The R groups are trans, but the two blue H's are both in front, two red H's are both in back, which means I've drawn this incorrectly. Now, H's are all the same. You would never be able to tell unless you did a specific deuterium. So let's say I did H2 here, but then I added D2, isotopically labeled hydrogen, then I'd be able to tell. And that's typically how they study these reactions, by using deuterium instead of H2, and then see where the deuterium goes. But these H's or these H's are incorrect. I just have to change one or the other. I've chosen to change those up there. So this same thing, the H's are wrong. So watch as they magically change. So now they're correct. Now those are trans, and those are trans, and the R groups are trans. So make sure that makes sense. That is really important. Go back and redraw how you go from here to here. Okay, gonna clear everything. And just make note that cis and syn addition should end up all the same side. Syn, 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 or cis, cis, cis. And if you rotate, cis, cis, cis would be, or I should say, syn, syn, syn would become trans, 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 or anti, anti, anti. Okay. Want to look at this? Same reaction or same concept, hydrogenating, but if we use sodium metal in the presence of ammonia, we get this concoction where we have NH2 negative and Na plus to balance it out, and an H minus, a hydride. So we end up getting a hydride reaction which can interact with this pi bond. And so when we treat an internal alkyne, we will end up getting trans addition. It's kind of weird that we get an H minus comes in, the negative here can pick up an H from NH3, turn it into NH2 minus, and so you end up with this anti or trans hydrogens. So I can add them cis using the Lindlar's catalyst. I can add them trans using sodium metal in the presence of ammonia. Apparently nobody decided to throw their name on this reaction. But thing to keep in mind is this is an acidic proton. In the event you try to do this experiment, this reaction on a terminal H, you end up just deprotonating it. So you end up getting this nucleophile. So this is that same reaction we just learned, that if you use a very strong base. You can deprotonate it, turn the nucleophile, and it can attack an alkyl halide. So this trans one only works on internal alkynes. If they have exposed H's on a triple bond carbon, it's too acidic, and it will get deprotonated. So it only works on internal. But something to add to your memorization, and that would be Lindner's catalyst, H2PT in a poison. We'll add the H as cis or syn addition, and then sodium with ammonia, we'll add it in a trans fashion. This becomes important if you have targeted stereoisomers. So if I need RR as opposed to RS, then I have to figure out whether I'm going to add originally cis or trans. So syn addition, anti addition. Okay, so just important to know. This one can work on internal terminal, so Lindler's works on everything. This sodium NH3 only works on internal, and it is an anti addition. Okay, hydroboration. So we did this with BH3 and peroxide. And if you remember, it added in an anti-Markovnikov fashion. So same thing happens here. If I do this, BH3, the BH2 is going to go here, H here. But because this is linear in nature, it ends up that it's not as selective as an alkene. So you end up getting far more Markovnikov than impurity than you'd expect. So it's imperative, again, that you do a 3-to-1 ratio of the alkyne to this. You form this compound, which they refer to, they being chemists, as an ene because it's double bond and an ol because an alcohol. So this is called an enol. An enol can undergo what's known as tautomerization. Tautomers are a special case of an isomer where if you look at this compared to this, you will note they each have a double bond, but double bond between carbons now becomes a double bond to O. The H that was here, the O, now has moved over to this carbon. So there's one more H I've not drawn in. This blue H is here. So this O and this H are accounted for in different positions in the double bond moves, known as tautomers. We'll go through the mechanism of how that works many, many times. So we'll just introduce this concept. So you can get an aldehyde by using BH3. But again, the problem here is that you have to add in a 3-to-1 ratio because this is linear. You don't get as much selectivity for the anti-Markovnikov as you do with an alkene. So there's a workaround. As mentioned, the first time the first H to interact, maybe in this case, again, I'm going to toss numbers out there that are totally arbitrary, but you might get, let's say, 40 Markovnikov and 60 anti-Markovnikov. Once you have one R group attached, then it's going to be a little bit better, but it's still a linear molecule. So the next one might be 70 anti-Markovnikov and 30 Markovnikov. And the last one we have 2 on might be like 90 to 10. And so overall, you still might only get 75-25. So you get too much impurity. So what chemists figured, well, why go through the first 2 additions when the third one's the most selective? So 9-BBN, 9-boro nonane, so and bicycloborononane. Basically what it is, it's a boron that only has one H attached. Okay, so still forms an enol first, and that enol tautomerizes to a carbonyl. In this case, specifically an aldehyde. And this is the 9-BBN molecule. So 9-borobicyclic borane. So a lot of names there, but we'll just call it 9-BBN. But notice what it is. It is an R group, and an H. It only has one H. So this is kind of like saying R2BH. So again, the first H is not as selective as second. Second is as selective as the third. So we're starting with just essentially the third H, the most selective one. By making this really bulky group, it's going to now put the bulky group next to the H. And so the boron will go here, causing the H to go there. So if I have my H connected to my boron is part of a bridging species. So I'm going to draw this in kind of a weird concocted fashion like that. And so that boron bridge is going to be found in the midst of that ring. So actually, let me emphasize that not quite the way I want to draw it. So it's more complicated, more like that. And so it will end up trying to get on the H side, which makes it much more selective. So 9BBN is just like BH3, but you skip to the third H uh, preference, which is driven by this crowdedness of steric hindrance, which makes it much more selective for anti-Markovnikov, which means much more selective for an aldehyde, carbonyl on carbon 1, than a ketone. Okay, so tautomerization. Want to just uh, show how this works? It can be done under basic, acidic, or biological conditions. So I'm going to just emphasize, because we're O-cheming, the basic and acidic. So under basic conditions, this enol, this OH, O on an ene, can get deprotonated. So let's choose OH minus. It can come and pull off that H, and in doing so, put a negative charge on that oxygen. That oxygen then can resonate in. It's not as favorable because negative would rather be on carbon, or on oxygen than carbon. But if it does that, notice this is a resonant structure. It's double-headed arrow because we haven't moved any nuclei. But now you have a negative on the carbon, which is less stable. So it's going to quickly pick up an H. It's going to come pick up the H and regenerate the OH minus that got us started, which means the OH minus is catalytic. It's going to be regenerated in the end. So the OH that we added in the beginning is regenerated in the end. And you have deprotonated. You made a bond, make a bond, break a bond, and then protonate. So deprotonate, make break, protonate, and you're all done. Very, very common type of mechanism. And we'll see this in bio. This would simply be an enzyme that's going to act in this way. So if you recall, enzymes, like any catalyst, go on in the beginning and are regenerated at the end. So it's catalytic in nature. So an enzyme could carry out the same thing in a biological condition. Under acidic conditions, we're going to have a similar thing, except now instead of deprotonating this OH making O minus, we're going to protonate, but we're going to protonate where the H belongs. So we're actually adding an H onto this carbon. So the first step will be to add there, so this double bond can come out, go after that H, and kick that up. So let me draw those arrows. So I'm going to protonate there, put that H on, the H we need. Now we have a carbocation here next to an O. This can easily resonate in. But in doing so, that's going to put a positive charge on O, which isn't necessarily the most happy scenario. But again, it's resonance, so we draw the resonance arrow. And last step, deprotonate. Now we deprotonate using water, not OH minus, because it's under acidic conditions. So basic conditions, we can have either OH or water, OH minus and water, acidic conditions, H3O plus or water. You cannot have positives in a basic condition. You can't have negatives in a acidic condition. It has to be either positive or neutral under acidic, negative or neutral under basic. So the water is going to come in, remove that proton, and once again, you have generated the material you started with. Your H now bonded to an O. So this same species here, this H2O picked up another H, and you have exactly what you started with. Okay, so this mechanism, have to know it. And you have to know it because it is a very fundamental mechanism that gets repeated in lots of other cases when we eventually get to alcohol or carbonyl chemistry. But this is our first step into it. So the enol we started with when we added 9-BBN to a terminal alkyne, that enol with the OH on carbon 1 turns into a carbonyl on carbon 1 known as an aldehyde. So an enol to a carbonyl. So this is an enol aldehyde resonance. Okay. Now we're going to keep peppering the alkyne with alkene reactions. So we did hydroboration, perfect. We did H2 hydrogenation, perfect. We're now going to do the mercury acid combination. So we did mercury with water in mercury acetate before. Now we're doing mercury with sulfate. So similar concept. Now we're going to add an OH. Because they're both equally substituted, because it's internal, the O could go to either this side, which leads to this ketone, or to this side, which leads to this ketone. So both ketones form, either adding an O to carbon 2 or an O to carbon 3. Methyl iodine, or methyl ketone, excuse me, forms, but no aldehyde. You do not end up getting, in this case, you end up getting it only there. You don't get it that side. And that's because mercury is going to bind to that side, which makes this the one susceptible to an O. So when you have an H and a carbon, then you have a choice. And in that case, mercury binds the terminal, which means the O is going to bind on the opposite side. Hydration of an alkyne. So in that mechanism, the mercury, before we had mercury acetate with an alkene acting as the electrophile with a plus charge, this time it's with a sulfate. So sulfate's -2, so mercury is 2 plus. So it's going to accept electron density. It's going to form that coordinated species that it just happens to do. It's going to have a full bond on the terminal side, but the internal carbon, it's going to have a coordinated bond, so not as strong. So delta plus is now being shared there. Water is going to come in and attack where there's a positive. When it does, you have an OH on that location. Another water is going to deprotonate it. And things are looking pretty good. We're kind of set. Last but not least, what under acidic conditions, again, that's why we have plus charges. This pi bond is going to come out and get that H. We are once again creating a positive charge there. It's going to resonate in. This carbonyl is going to get deprotonated. And then it's a matter of just removing the mercury. Notice it magically sort of happened. It ends up that you're going to end up putting an H on that carbon. So when this goes on, you're going to lose that pi bond there, and your ultimate, because of the ketone formation, the tautomerization, you're ultimately going to put an H back to here later on. So that's just the emphasis I want to put in. So for now, this H is this one, but want to emphasize that this is getting you to the enol. Eventually, you're going to turn it into a ketone. It's going to undergo tautomerization. But for this, I should just focus on this, that you end up losing these electrons, you regenerate the He2 plus you had in the very beginning. So He2 plus went on, and it is regenerated in the end. Okay. So we have done alkene reactions that we learned in previous podcasts, and now applied them and made them alkyne. So it is always important to keep a running log of things. So in the next podcast, we'll get into our spider chart, and we'll toss a couple more alkene reactions at alkynes and see what happens, and find that most, but not all, of the reactions we use in alkenes will work on alkynes. So with that in mind, thank you for enjoying yet another wonderful podcast, and I will see you in the next one. Bye.